Oh, here we're having a look at vectors. And the thing with vectors is that, and we've discussed some of these things, so I'm going to just go through the vector stuff because we didn't mark that last question, and then I just want to have a look at this sort of setup. So you must be able to do a free body diagram. We discussed that. We said that all objects will be represented by a dot pointing away from the dot, and then you must fully label all of your forces. For example, force applied, force of tension, you can have force of friction, you can have force of air resistance, force of the normal if it's on the surface, force of gravity. Sorry, just put this over here. FG, or you could say W, or you could say MG, right? Whatever the case is, you need to label. Then we discussed resolving into the x-axis and into the y-axis, and we said that if I'm looking at fx, I've got to go f cos theta, and if I'm looking at the perpendicular one, I've got fy, which is f sine theta. Alright, so that's your components. Then calculating your resultant force and your net force. Don't forget we need Pythagoras and tan theta. Always use 10 because that's probably the information they're giving to you. And then it helps us to get more easily, it helps us to get more easily to those answers in terms of the resultant vector. So what I'm going to look at now is I'm going to look at that example that we didn't get to mark, the one with the angel in the wings. And we're just going to have a look at how you address an issue or a question like that question. Alright, so I'm just going to add this in. And this is what we're looking at. So what I've got here is a school is hosting a play or a drama evening. One of the characters is an angel and must be suspended in the air during the production. A cable and a rope are attached to the student's harness. The cable is lifting vertically upward at 40 degrees. And a student on a ladder in the wings is pulling horizontally. The angel has a mass of 40 kilograms. So this is your little setup over here. So what they want you to do here is calculate T1 and T2. Alright, so let's have a look at how we're gonna deal with that situation. Alright, the first thing that I like to do, and I'm in the habit of doing this because it helps me to see what situation I have in front of me. So I'm going to draw a free body diagram, and what I've got here in the middle is I've got my object, and pulling from the wings, I have one force. I know that at 40 degrees, I'll try and be as accurate as possible. There. At 40 degrees, I've got another force. And then coming down, I've got that situation in front of me now. Alright, so over here, I've got my T2. Over here, I've got T1. And 40 degrees here. Right, and that's pulling this way. And down, I know I have my mg. And at this point, I know that mg is equal to 392 newtons. So now that I've sorted out my situation, I need to just have a look here. In this situation, if I look at T1, right? T1 has two things happening. Number one, there's a lifting force there. So now I'm ending up with FT1, right, in the y direction. So it's going upwards. I also know of T is that it's moving Fx towards the left. right? I also know that T2 doesn't have any vertical forces, so no y direction. That means that the y direction is only between T1 and mg. So first of all, let me just take account of my forces. If I think of vertically, right, I'm looking vertically, I have T1 and it is upward, and that upward force is not shared with T2. Therefore, T1 is actually equal to mg. So T1 is then equal to 392 newtons. Guys, when I say mg, I'm talking about Fg, which is gravity. It's up to you how you're going to label it. And I prefer just writing mg so I know what I'm doing. So I've got this T1 and it's a lifting force, right? So the first thing now, or the first problem is, if I look at T2, right? I have no apparent information, but I do know that Fx1 is equal to T2. Now, for T2, I have no information. But I do have information of Fx. Because in this Fx triangle here, in this triangle, I've got the 40 degrees, I've got the T1, I've got the Fy1, I've got so much of information. So what I'm actually going to do is, when I'm doing my calculations, I must realize that if I can solve Fx here, then I would technically have T2. So now the next step that we have to do is we need to solve for T1 and T2, essentially. Alright, so the best thing to work with now is to sort out my T1 because I've got information for T1. So a little triangle situation that I find helps me when I do these is I try and simplify my life a little bit better by drawing these triangles, because then I don't have to manipulate formulas to get whatever I need. Oh, sorry, what am I doing? That's 10 over A. Right. So T1, I have right now the opposite, which is 392. And I've got my theta at 40 degrees. So essentially, I don't have my hypotenuse. So what I'm going to say is sine theta is equal to opposite over hypotenuse. I know that hypotenuse is actually equal to opposite over sine theta. So my opposite is 392 divided by sine theta, which is sine 40. And I'm going to end up with 609.84 newtons. And there we go. I've now got T1 is equal to 609.84 newtons. So there's my first answer. Done. Right. The next thing that you need to sort out is T2. Right. Now we know that Fx1 is actually equal to T2. Right. As the object's not moving, the adjacent is equal to the adjacent because of equilibrium. So all you're going to do now, instead of solving for T2, you're going to solve for Fx1. Now, if that's an adjacent, all I know is that cos theta is equal to adjacent over hypotenuse. And if I'm looking here, I want adjacent. So I can see what my formula is going to be. And my formula is going to be, adjacent is equal to cos hypotenuse times cos theta. Now I've got my hypotenuse. I've got my hypotenuse from the previous question, which is 609.84, multiplied by cos, multiplied by 40 degrees, and my adjacent in this situation is 467.16 newtons. And now, therefore, T2 is 467.16 newtons, because this adjacent that we looked at here was that setup. So now I've got my two answers, and you'll notice that if I'm looking here, they can ask you a question and say, comment on the difference in the magnitude of the two forces. You can say that T1 is bigger because it has a lifting force, and lifting forces are in the opposite direction to gravity. So in order to lift something, you must overcome gravity. And because gravity is such a big, or it has such a big magnitude, it is quite difficult to get through to that. So that is why T1 is bigger than T2, and T2 only has a pulling force. So when you're doing these types of questions, make sure you work with some sort of system. Alright, the next thing we're going to look at is we're going to look at Newton's laws. I'm going to go through Newton's laws in terms of 1 and 3, and then from 1 and 3 I'm going to move on to 2. So you'll see that when you're done with this video, the handout that I gave in class, it's uploaded in this folder, so you don't have to worry about that. If you didn't get a copy of it, you'll do the activities, the one with the school bus and the elephant and the football and the feet, and then the other one you'll do with the astronaut and the cannon and so on. So once you're done with those, send them to me. I'll send you guys a memo for those, and then afterwards I want you to start with Newton 2, right, which will be a separate video. And so in the previous chapter, you have looked at forces and how we can represent forces as vectors, and you look at different types of forces and how objects on Earth experience those forces and the interaction of the different objects. So when we look at Newton's 3 laws of motions, we're looking at dynamics. And this branch of mechanics looks at the motion of bodies, objects, systems under the action of forces. So the motion of an aircraft through air can be explained or described by physical principles discovered over 300 years ago by Isaac Newton. And Newton worked in many areas of mathematics and physics, and he developed theories about gravity in about 1666, which at that point he was only 23 years old. So possibilities are endless. And because you're young, it means you have that kind of talent and brain capacity to discover these things. And before Newton, there was Galileo, and he was actually placed under house arrest because back then science was kind of illegal. So he looked at how things will move and continued moving if nothing else interferes. And he kind of brings up a basis, or he sets a foundation for Isaac Newton then, so that he can do more experimentation with those ideas, so he can confirm what Galileo had assumed. And before him, the Greeks, they only thought the types of motions were natural and violent. So about 2,000 years ago, they thought that if you threw a rock up, it would come down because it wanted to be close to the earth. Or the reason why fire goes upwards is because it wants to be close to the sun. Heck, they thought that fire was made from the sun. So things were kind of medieval back then. And without people like Galileo and Isaac Newton and Albert Einstein and Nikola Tesla and all of these discoverers, we wouldn't be where we are today. So the importance of a topic like this is about understanding these individuals and how they see in the world, and how their experimentation has led us to the point where we are in the 21st century, in 2021. So the first thing I want to look at is types of forces, and just get familiarized with those ideas if you may or may not have forgotten. Right, the first type of thing is you have non-contact forces, which are called field forces, and then you have contact forces. Right, so there must be some sort of touching that happens there. So the first force that we look at is a gravitational force. When we look at a gravitational force, we know it's towards the center of the object, and that object has mass, which means that leads us to Fg, which is also equal to the weight of an object, which is equal to the mass of the object multiplied by 9.8 meters per second squared. That's your gravitational acceleration, and that whole thing is downwards. So you'll see that we'll use the symbols mg for weight and w for weight in terms of symbols. Alright, then we have the normal force. With the normal force, you deal with it quite a bit in these situations. It's always perpendicular to the surface. How we symbolize that is by using Fn, or you could write F normal if you want as well. Right, the next one we look at is friction, and we know with friction is always parallel to the surface in the opposite direction of motion, and we're going to use force of friction like that, or just simply a little F. Now with friction there are two types. We've got static friction and we've got kinetic friction. Kinetic friction. Alright, what's static friction? This is if the object is not moving. Alright. Usually with static friction, it's on surfaces that resist motion. Right. Kinetic, it means your object is in some sort of motion. So the symbols we use for static friction is Fs, and it gives us the formula mu s times Fn. And for kinetic friction, it's Fk, which gives us a formula mu k times Fn. And at this point, you should be able to identify whether it's a static situation or kinetic situation. And this symbol here is a mu, right? And it stands for the coefficient of friction. The coefficient of friction. Now, when we work with the coefficient of friction, the coefficients of friction start at 0, where you have no friction, and the value goes up to the number 1, where you have a lot of friction and no movement. So if you have to be asked to work out the coefficient of friction, it should be between the numbers 0 and 1. In some instances, when we do it at school, at a school level, you might get something like 2 as your answer. Right? And then that you should be able to identify that there's something wrong, and you'll have to explain why it's incorrect. Fn here is the normal force, which you'll get from your information. Don't forget, the normal force is usually equal to Fg, because the normal force is this way, Fn usually, and Fg is that way, then they're usually equal to each other. So to get the normal force, you just look at your Fg or your F perpendicular, right? One of those values should give you your normal force, so it's not so bad. The next thing we have is an applied force. Now, with applied forces, there's two types. There's the push or pull, and we'll call that F applied, right? There's also in a string situation, and when the string is pulled, T-A-U-T, taut, we have force of tension, or you can write that as force tension. How this works is if we have some sort of string, right? Force applied or force of tension usually gives us our motion, or it gives us some sort of acceleration that we can work with there. Right, the next thing we have that you're going to need to know, the other forces you get actually are spring forces, buoyancy, we've got magnetic forces, electrostatic forces, but at this point, these are the important ones. We also need to make sure that we know our trig ratios, right? I'm sure you've done this in maths. So know your trig ratios. You also need to know forces on an incline. Right, forces on an incline. If I want Fy, or rather, let's put it like this. If I want F perpendicular, my formula is mg cos theta. And if I want F parallel, that's going to be mg sine theta, right? Also, we must realize where theta is. The theta angle is always between FG perpendicular and the hypotenuse. So therefore, we'll be forced to use tan theta is equal to opposite over adjacent. And those are all the different types of forces that will be working here. Remember, when we have forces on an incline, there is no Fg. Mostly because Fg is actually F res. And because of that, I must sort it into the components. But we'll get to all of that as things progress here. And now we're going to look at Newton's laws of motion. Let's start with the third law, and then from there we'll move into some theory and so on. Newton's third law of motion. So when you do the section, these are the requirements that you will have to complete in order to finish this. So the first thing is you need to be able to state the law. When object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. So basically, if object A exerts a force on object B, then object B will exert an equal force on object A. So basically, for every action force in nature, there has to be an equal and opposite reaction. So if this goes for everything. Now, in this thing, you must be able to understand the properties of an action-reaction pair. They must be equal in magnitude. They must act in opposite directions. They must act on, and this is the one that's weird, different objects. And they must occur simultaneously along the same line. So that's the kind of information that you need to make sure that you can retain by the end of this, and hopefully I can help you to get there. Alright, so it's a bit of a mouthful, but what he's getting at here, Newton, is that the forces are not singular. They exist in pairs called action-reaction pairs. Right? And one of the most common action-reaction pair that we look at a school level is a book on a table or any object and the earth. So that's what we're going to look at now. So if I ask the question, what forces act on this object. Right? The first thing I've got to look at here is, because I know gravity exists, I know that this book in some way is attracted. So we know that the earth, because of its gravity, exerts an attractive force which we call weight. So that's the first force, right? We also know that this book, as I'm looking at it, it stays on the table. Now I want you to hold out your hands in front of you. Try this, right? Hold out your hands in front of you. Take your left hand and face your palm to the ceiling. And then take your right hand and place it on top of your left hand. Now what you would create there is like a crocodile. So your arms look like the jaws of a crocodile. And what I want you to do is, with your top hand, I want you to push down. And what you'll notice is, even though you want your other hand to push down, your bottom hand, no matter how weak you make it, if it's stretched out and you're pushing down, you will feel that your bottom hand is still pushing upwards. So if your right hand pushes down on your left hand, you will notice that your left hand has this need to resist. Because you're pushing down on this object, the other object is pushing up. So if I'm looking at this book on this table, and this book is staying on the table, that means, and it's not falling through the table, it means that my surface is pushing up. So I have the surface back upwards on the book. So what is I've got essentially is, going this way, I've got this upward force, and my book is going down. So this is the earth on book, and the other one is the book on the earth. So what you would notice now, if I'm looking at this situation, the two forces are not acting on the same object. Right? They are not acting on the same object. So you cannot draw free body diagrams because free body diagrams only represent one object, whereas Newton's third law, we have two objects and they are each reacting with one another. So if I had a situation, let's say I had a situation where I had a fish moving through water. Right? I have a fish moving through water. Now how that happens is, that fish needs to move parts of its body. So let's say the fish, sorry, this is my sad attempt at a fish. Right, let's say my fish over here. My fish needs to move forward. That's what it wants to do. Now, the only way that it's going to move forward if it uses its fins. So what happens is the fins of the fish push water backwards. Right? So it pushes the water. So if I had water here, it pushes this way. And by pushing backwards, the fish moves forwards. Now these forces, we can see they're opposite in direction. And you must also note that they are equal in magnitude. That means they're equal in size, if you're forgetting what magnitude is. All right, so your action here is this. The fish pushes the water backwards. And your reaction is that the fish moves forward. So if I think of another scenario B, the motion of birds, particularly their flight, and how does their flight happen? So a bird flies. I'm going to draw a bird. A bird flies using its wings. The wings, so action, push down on air, right? And the bird moves upwards. So your action is the wings. Your reaction is the motion of the bird. So without these action-reaction pairs, birds wouldn't be able to fly. Here's a more common one that we see often. The wheels on a car, right? So when you drive to school in the morning, and consider the fact that the wheels need to spin in order for the car to move. So what you're looking at is, when you look at the wheels, a lot of the time it looks like the wheels are moving forward. So when I'm looking at a wheel, right, I'm looking at the wheel, I assume that my wheel is going in this motion, which it is technically. So I would say it's moving forwards. So with the wheels spin, let's say here is the surface. Now your surface has friction. So what needs to happen is, for the wheels to move or spin, they must grip here. Let me use another color so we can see that a little bit better. They must grip here on the surface of the road, and they must push backwards. So actually they're moving like that. So you assume the wheel's moving forward. It's not. It's pushing backwards. So in terms of your action, right, your action-reaction pair, the wheels push backwards on the road, and the reaction is that the road pushes the car forward. So you can do this with your feet as well. Watch when you're walking. Your legs or your feet are moving backwards. They grip onto the ground and they move backwards, and your body propels forward. So that is your action-reaction pairs. And you need to be able to identify, and sometimes there's multiple, there can be up to 6 or 7 action reaction pairs on one single situation, because your forces are not actually acting on the same object. Alright, so if I can do this also with non-contact forces. Let's say, for example, let's look at this one. Let's look at the sun and the earth. This is a non-contact, right? So if I have my sun here in the middle, and then I have my my planets that are orbiting the sun, and then somewhere in this orbit I've got Earth. Alright, so I've got Earth over there. And the sun needs to hold the Earth in position. So the sun, because of its gravity, holds the Earth in position. Right? In a pulling manner. So it's pulling now, right? So I've got force A on B. Alright? At the exact same time, your Earth is being held in that position a certain distance from the sun, as if it is holding onto the sun. So on this end here, so the first thing is that setup. The Earth is being held at a certain position. Oops. It's being held at a certain position. Right? It's almost as if it's holding, like I said, holding onto the sun. Right? So now I know there's a force from the Earth on the sun. Let me just label these so that we can see what's A and B. This is object A and this is object B. So essentially now I've got my action, which is A acts on B, and I've got my reaction, which is B acts on A. So you must note that we're working with two objects, not just forces acting on one another. The responses of the objects and their forces always are qualitative. So when we do this section, we say it's qualitative. And qualitative means we need to know theory and we need to know how to explain the theory. And we need to know how to state the law. You will need to memorize Newton's third law and be able to explain its links and relevance to certain scenarios. There are no calculations involved in Newton 3. Alright, so when we're looking at Newton 3, make sure that you understand that everything comes in twos. So when you're dealing with Newton 3, it's easy to work with them because there's no real changes. Everything's equal but opposite. These forces that come in pairs, they come in twos, so that's all sorted out. But what will happen when only one force acts on an object, or we have only one object and all the forces are acting on those objects? So this leads us to two situations. So the first situation is this one. If you have a resultant force that is greater than 0, right? This means that the object will move in the direction of motion or the opposite direction of motion. Right? So in this sort of situation, your free body diagram would look something like this, where you've got your force applied here, force of friction, your Fg/mg situation over there, and it will move. And that gives rise to Newton 2. Right? So we're going to get there. If you have an object and all the forces are equal, so your resultant force, your second situation, if the resultant force or F res is equal to 0, that means that the acceleration of the object is equal to 0 meters per second squared. It means that it's moving at a constant velocity, essentially, right? In that situation, and my resultant vector is equal to 0, then I can say that this situation is in equilibrium, right? And if it's in equilibrium, then my F res has a 0 resultant force, and that gives us the section of static equilibrium. So this is if the object, there's no movement, and we discussed this when we did static equilibrium, or the object is moving at a constant velocity, its speed is the same all the time, like when you're moving on the highway at 120 kilometers per hour. So if I do have single objects, those free body diagrams can look one of two ways. When we work with Newton 2, we're going to use this type of free body diagram. When we work with equilibrium, we're going to use this type of free body diagram. So that's how the Newton's laws differ from each other. So the video that you have on, according to Newton's third law, the one with the school bus, and it says check your understanding about the reactions. It has the school bus, the elephant and the man, the elephant, the tractor and the man, the football and the feet. I want you to go and do that worksheet. So stop the video, go and do that worksheet. See if you can handle all of those scenarios in that situation. And then when you're done, send me your solutions. I'll send you the memo before you continue with the rest of this video. Because the next thing we're going to get into is Newton's first law. So please make sure that you get that done, so that you don't have an information overload, and that while it's fresh in your mind, you have the opportunity to go and practice. The law we're looking at now is Newton's first law of motion. So when you're looking at this section, you will need to make sure that you know how to state the law. And the law goes like this. Newton's first law states that an object continues in a state of rest or uniform motion, or uniform velocity rather, unless it's acted upon by a net or a resultant force. So essentially every object is going to remain at rest, which means it's not going to move. There's no movement. Or in uniform motion, which has a constant velocity in a straight line, unless acted on by an external force. So this is an external force. Right. So when we talk about external forces, we're talking about objects that will keep doing what it's doing unless something on the outside must come and interfere with it. So if I leave a pen on a desk or a laptop on the desk and I leave it there and it sits there, it will stay there until someone comes and picks it up or I pick it up. And the same as if a car is moving at a constant speed of 80 kilometers per hour and there is unlimited petrol, no brakes, no traffic lights, no stop streets, pedestrian crossings, nothing. It will drive and drive and drive forever. So things will keep doing what they're doing if there are no forces acting on it. Right? So if there are no forces acting on it, it will do what it's doing. That sounds silly, but in basic layman terms. If it's moving though, it will move in a straight line. It will move in a straight line, no turning. The reason for that is, if I'm saying that there's external forces, I need to understand what do those external forces do. So if I have external forces, they can do three things. The first thing they can do is they can slow it down, or they can speed the object up. And the last thing they can do is they can change direction. So when we're looking at these scenarios, you need to make sure you look at the external force and what effect it has on the system. Now, on Earth, we don't have conditions which make this law perfect in practice, mostly because Earth is not a vacuum. Right. And what this means is, if I'm in a vacuum, it means I'm in outer space. And in outer space, there is no matter. Right? Now, Earth has matter and atoms and molecules and so on. Right? So when we look at Earth, we will look at scenarios where we have external forces. When we do Newton 1, right? When we have these external forces, we can see how these external forces will affect each scenario. So, if I look at number 1, when you kick a ball on a pitch, right? When you kick a ball on a pitch, it will roll and roll and roll and roll. And then it will stop. But no one will touch it. Why does that happen? Right? So when you kick a ball, it rolls until it eventually stops. Now the reason for this stopping here is because if you think of a football pitch, we have grass. And grass is not a smooth surface. Right? So we know that on grass we will have friction. So therefore, there is a coefficient of friction between the ball and the grass surface. So that's what's going to slow it down. If you look at the second scenario, if you're in a car, right? Now, if you're in a car, there's two situations. There's the city and there's the country, right? So when I'm in the city, you have options where you accelerate, right? So you start off slow to fast. You decelerate. You go from fast to slow, right? When you're in the city, you stop often, So no velocity. You can go in reverse. You're in a situation where you apply brakes. You apply brakes, you go in the opposite direction of motion because you're slowing down, right? So you're in the situation where, and often what happens when you in the city is you're making constant turns, right? You can either go to the right, you can either go to the left, you can take a turn that looks like that. Whatever the case is, you always, your velocity is not constant. But if you're in the country, and let's say you drive into places like Drakensberg or Eastern Transvaal or Durban, wherever the case is, if I have longer roads, longer, clearer roads, I can achieve a constant velocity. Because in these situations, there is no reason to brake in a hurry, no reason to slow down, or even have to speed up. Essentially, if I have a constant velocity, that means that all the forces are balanced. And if all the forces are balanced, I'm in equilibrium. And I know about equilibrium, the acceleration is equal to 0 meters per second squared. Right? So if you're in a car, you can have two different types of situations. Right? One of the more life-threatening ones that we deal with in physical science is the seatbelt. And I'm sure you've done this one before. Now, seatbelts provide a safety service. Right? And the purpose is to slow you down. This can either happen gradually, and it mostly happens gradually because when you come to a stop, you don't always come to a sudden stop. And emergency purposes, it tries to slow you down as quick as possible. And I'm pretty sure you've seen the safety clip, that if you pull the seatbelt too quickly, it jams so that it can protect you, so that when you get into the car and you're in one of these situations, you don't go through the windscreen. So here's what's happening. When you get into the car, you and the car, so when you're in the car, you and the car become a system. So in terms of mass, it's going to be mass of the car plus mass of the human. Whatever the car experiences, so will you in terms of motion. So when you're in the car and you're moving, suddenly your mom or dad or you brake, you will notice that the coins in the car, the ashtray, the things in the boot, the cups, the holders, or the garage remote will all move around. So the reason for that is, if your car is moving at, let's say, 140 kilometers per hour, so if the car moves, right, that means that you, the driver, the keys, bags, and everything is also moving at 140 kilometers per hour. Now, when the driver hits, so that's the situation, then the driver hits the brakes. Right? Now, the brakes only affects, let's say the car, only affects the car itself, right? But everything else inside the car continues moving at 140 kilometers per hour, even after the brakes. So that means if you aren't wearing your seat belt, you're going through the windshield at 140 kilometers per hour, or you're going to hit the back of the driver or passenger seat at the same speed. That's why when you hear things of like died on impact, it all has to do with momentum and Newton's laws. And then the minute that happens, you die. Because what's going to happen is you're going to hit that windscreen at 140 kilometers per hour. You're going to go through and through. Or when you hit that glass, you're hitting it with a force. And remember from Newton 3, object A on object B on object A. So you end up in that kind of situation. Now this whole thing, and you've dealt with it last year, is called inertia. So when we're looking at inertia, we can relate Newton's first law. So Newton's first law, we can call the law of inertia. When we look at the law of inertia, it means that all objects that just don't want to move because they have inertia. So when we talk of what inertia means, we're looking at it is the resistance an object has to a change in its state of motion. Now the reason why objects resist is because this resistance is because objects have mass. So when we look at inertia, if an object has some sort of mass, it wants to keep doing what it's doing. So inertia is related to mass only because if I have a bigger mass, I'm going to have a bigger inertia. All right? Please note that inertia is not a force. Right? It is a property related to mass of objects. So if something has a large mass, something has a larger mass, it is more likely not able to move in some sort of hurry. Now we use the quantity of mass to measure the amount of inertia an object has against a change in motion. The more mass an object has, the more force it takes to change. So here we can say the more force it will take to change its state of motion. Right, so the second thing that you need to go and do, or the second activity that you're going to do, is the other worksheet that I gave you, the one that has an astronaut and a cannon on it. And it's Newton's first law. It's a whole bunch of scenarios. And then what you've got to do is you've got to discuss there, in terms of Newton 1, how do those objects move? And then after you do that activity, please make sure you send that activity to me so that I can send you guys the solutions of that one. And then once you're done with that, you can go watch the second video, which is called Newton 2. And what you would have noticed by now is that Newton 1 and Newton 3 do not expect you to do any calculations. Rather, they require an understanding and application. So these exercises need to be done so that it can give you a better idea how to answer Newton 1 and Newton 3 questions. And then you can move on to Newton 2, and that's where we start all the calculation. So this is the end of this video.